going to talk in this lesson about inclines and forces on objects that are on an incline. An incline is actually just a fancy way of saying straight hill or ramp. So you can think of it as either of those things, like a hill or a ramp. Okay. And the best way for me to explain how to deal with forces on objects that are on inclines is just to go straight to an example. So that's what we'll do. Okay, so in this example, let's say we have an incline that is at 30 degrees with respect to the horizontal, and we're going to have this crate that we want to push up the incline, and let's say it is a 10-kilogram crate. And for this first example, we'll say that there's not any friction. Perhaps this is one of these ramps that has rollers on it, or perhaps our crate has wheels underneath. So we don't have to worry about friction in this example. But we're going to push this crate up the ramp, and we want to find what force is required in order to push the crate up the ramp at a constant speed. Okay, so what force do we need? To push the crate up the ramp at a constant speed if there's no friction. And you can solve these problems using the same problem-solving technique that we've talked about before, where you read the problem, you draw the situation, which we've already done, and then you draw a free body diagram. So let's draw a free body diagram of our crate. Here's the crate. Okay, the different forces that we have on this crate. We have the force of the push. I usually draw all of the forces as originating at the center of the object. You don't have to draw them that way, but that's generally how I draw them. We have gravity pulling straight down on the crate. And we have the normal force of the plane on the crate. And remember that the normal force, by definition, is always perpendicular to the surface of contact. So in this case, the surface of contact between the crate and the plane is that red line right there. So if there's a force that's perpendicular to that, it's going to go up like that. All right, so that this and this are both right angles. So my normal force is going to be up like that. And those are the only forces that are acting on the crate, since we don't have any friction. Okay, next, we need to resolve the forces into their X and Y components. In order to do that, you need to pick an XY coordinate system. And here, to the extent that there is a trick for this kind of problem, this is it. What you want to do is you want to pick your XY coordinate system so that the X direction is parallel to the plane and the Y direction is perpendicular to the plane. So this is X and this is Y. The reason we do this will become a little bit more clear in a moment, but the short answer is that it makes the math much, much easier if we draw our coordinate system this way. But one of the advantages of drawing the coordinate system this way is you can see that we've got the normal force and the force of the push. The normal force has only a y component, and the force of the push has only an x component if I draw my coordinate system this way. Gravity, on the other hand, has both an x component and a y component. Now, I know it's kind of weird to think of gravity as having an x component, but in this case it does. This will be the y component of gravity, and this will be the x component of gravity. Okay. All right. Now, we need to resolve gravity into its x and y components. So in order to do that, we need to know one of the angles inside that triangle that I just drew. It turns out you can show with some simple geometry, and I'm not going to go through that geometry right now for the sake of time. I want to get on with the example. But that angle right there is the same as the angle of the incline. It's 30 degrees. Okay. So we'll mark that as a 30-degree angle. So if I want to find FGX in terms of FG, it's going to be FGX is equal to the hypotenuse FG times the sine of 30, because the x component of gravity, all right, this line right here that I'm making thicker, that is opposite to the 30-degree angle. That's why I'm using sine, even though it's the x component. And then FGY is equal to FG times the cosine of 30. Okay, now we have finished resolving all of the forces into their x and y components. So next, step 5B in our problem-solving strategy will be to apply Newton's second law in both the x and y directions. Sum of the forces in the x is MAX. Sum of the forces in the y equals MAY. And so now let's take all the forces that are in our free body diagram that have an x component and put those x components on the left side of this equation. We have the force of the push in the positive x direction, and we have the x component of gravity, FGX, in the negative x direction. Those are the only forces in the x direction. Okay, now that is equal to m, the mass of the crate, times the acceleration of the crate in the x direction. But remember the problem statement. I want to go at constant speed, which means the acceleration is 0. In other words, adding FGX to both sides, the force of the push that I need is equal to the x component of gravity. The x component of gravity is Fg, which is mg, times the sine of 30. The mass of the crate is 10 kilograms. G is 9.8, and sine 30 is a half. So you end up with 1/2 times 9.8 is 4.9, times 10 kilograms is 49. the force of the push that we need is 49 newtons. In this example, we didn't even need the y direction because there was no friction. And that was the advantage of picking the x and y coordinates like we did, because the push had only an x coordinate, so we didn't even have to worry about the y direction. That won't always be the case. Sometimes you'll need both x and y directions. But always, whenever you have an incline, you should always pick your x and y axes like I picked mine in this example. Okay, I'm going to clear this page now and work another example, this time on an incline that has friction. All right, this time, let's say we have a hill. Again with a 30-degree incline. And let's say that we have parked our car on this hill, but the hill is icy, such that the coefficient of static friction between our car's tires and this icy hill is 0.3. Okay, and the question is, will our car slide down the hill if we park on the icy hill? Well, we approach this like we do all of our other free body diagram problems. Sketch the situation, read the problem, draw a free body diagram. Here's our car. Okay. Let's draw the forces that are acting on the car. I have gravity straight down. The normal force perpendicular to the plane. And friction parallel to the plane, pushing uphill, trying to prevent our car from sliding down. The only question is the friction going to be strong enough to do that? Those are all the forces that are acting on our car. So next we need to pick a coordinate system and resolve all of the forces into the x and y directions. Once again, because we're on an incline, we're going to pick the y direction to be perpendicular to the plane and the x direction to be parallel to the plane. So this is the positive x direction and this is the positive y direction. All right, well, because we've picked our coordinate system this way, the normal force has only a y component and the friction force has only an x component, but we need to resolve gravity into its x and y components. This and this. Okay, well, this time I will show you how to find the angles inside that triangle. So what you need to do, let's see, let me pick yet a different color. Let's go ahead and draw this horizontal line right here. This has to be 30 degrees because it's the angle of the incline. This angle is 90, meaning this angle is 60. If that angle is 60, then this angle that I have marked in purple must be 30. Okay. So the purple angle, which we'll call theta, is 30. Okay, now we do what we always do next. After drawing the free body diagram, I need to find the x and y components of all my forces. Normal force has only a y, friction has only an x, but I need FGX, which will be equal to FG times the sine of 30. And I need FGY, which is equal to FG times the cosine of 30. Once you've done that, you apply Newton's second law. The sum of the forces in the x direction equals m a x. The forces in the x direction are F G X in the positive x direction and friction in the negative x direction. That is equal to the mass of the car times the acceleration in the x direction. FGX, I know, is mg times the sine of 30, and the sine of 30 is a half. Friction is the coefficient of friction, mu, times the normal force. That's equal to MAX. Well, we're temporarily stuck because I don't know the mass, I don't know the normal force, and I don't know the acceleration in the x direction. So I've got three unknowns and only one equation. I need another equation. Let's get that other equation from the sum of the forces in the y direction equals MAY. Forces that I have in the y direction include the normal force in the positive y and the y component of gravity in the negative y. That equals the mass of my car times the acceleration in the y direction. Well, the acceleration in the y direction must be 0 because the y direction, look back up in my original drawing, that's the y direction. So if the car's accelerating in that direction, that means it's starting to levitate above the hill or maybe sink down into the road. Well, neither of those two things is happening. So the acceleration in the y direction is equal to 0. That means that the normal force is equal to the y component of gravity, or the normal force is equal to mg cosine 30. Let's take this expression that we got for the normal force and plug it in right there. Okay, G is 9.8, and if I multiply that by a half, then I get 4.9. So we have m times 4.9 minus, all right, well, mu is given in the problem as 0.3. So let's put that down as 0.3. The normal force, well, we just proved that the normal force is mg times cosine theta. Cosine theta is 0.87. Okay, and that has to equal MAX. Well, hey, I have an m in all the terms now, so let's divide both sides of this equation by m. That means this m cancels, that m cancels. I'm going to go up to the top now because I'm running out of room at the bottom. So we now have 4.9 meters per second squared minus 0.3 times 9.8 times 0.87. So let's do that on our calculator. Okay, 0.3 times 9.8 times 0.87. And I get 2.56. So that term is 2.56 meters per second squared. That is equal to AX. 4.9 minus 2.56 is equal to 2.34. So the acceleration of our car in the x direction is 2.34 meters per second squared. That is the positive x direction, and the positive x direction is down the hill. So unfortunately, the answer to the question is yes. Our car is going to slide down the hill. If you wanted to figure out the acceleration that your car would have, it actually would not be 2.34 meters per second squared, because we used, to solve this problem, we used the coefficient of static friction. But once it starts to slide, the correct coefficient of friction would be the coefficient of kinetic friction. So you then need to rework the problem, doing everything we just did, except you would replace your coefficient of static friction with the coefficient of kinetic friction, and then you would have the acceleration that your car would have. All right, that's the end of this lesson.